Okay, so real quick, let's just have a quick summary of what uh, this lab is all about. So pretty much in this lab we have an ultrasonic sensor, which is the HCSR04 sensor module, right? So this here is our ultrasonic sensor, which has basically two parts. So it has the transmitter, the receiver, and then the circuit that does all the functions. So pretty much the transmitter, right, is going to send out some type of sound waves, and it's going to bounce off of an object, right? It could be any object, and it essentially reflects that back into the receiver, right? So it's just basically like using ultrasound, like using ultrasonic waves. So yeah, that's pretty much it. And then essentially what we want to do in this lab is our overall goal is to find the distance between the sensor and that object. So yeah, pretty much in this lab we're going to be looking at how to do all those all that calculations and everything. So how to determine this. So pretty much for the first two experiments, what we're going to do is we're going to essentially um, set up the necessary components in order to make the sensor module work. And then at the end, in experiment 3, what we're going to do is we're actually going to see this all come together. And yeah, so essentially experiment 1, experiment 2 are just setting it up, setting up everything that we need, and then experiment 3 is the actual main part. So yeah, let's get to it. Okay, so for this experiment, pretty much all we had to do was set up the UART. So, and essentially first here, as you can see in our code, we first have to define the baud rate divisor integer and the baud rate fractional part. So first we need to calculate those two values in order for them to use in our code. Now, the given information that we have is that the UART is 38,400 bits per second, and then that our divisor is 8. We're going to use the divisor to be 8. Okay, so now let's do that. Okay, so now let's see how to find the UART IBRD and the UART FBRD. So what do these mean? So essentially, the UART IBRD is essentially the UART integer baud rate, and then this one is the UART fractional baud rate. So baud rate divisor, right? These are the baud rate divisors, the two parts of the baud rate divisor. So now let's see how to calculate. Okay, so the first equation that we have is that our UART frequency, so our FUART, is equal to the system clock over our divisor, right? And if we recall, the given information says that it was the system clock is 80, right? It's 80 megahertz, and the divisor was 8, right? So we have 80 megahertz divided by 8, we get 10 megahertz, right? 10 megahertz. Okay, cool. Now that we have the 10 megahertz, the other equation that we're given is is essentially that our baud rate divisor, right, our baud rate divisor is equal to the frequency of the UART divided by the baud rate. Okay, so our baud rate divisor is equal to our our FUART, right? Our FUART divided by our baud rate. And as you recall, the baud rate that was given was 38,400, right? So, and then our FUART, which is what we found up here, is the 10 megahertz, right? Okay, so cool, right? And then now what we want to do is we want to find our baud rate divisor, right? So if we solve for that, essentially the number that we get is, it is, give me a second, let me plug it into my calculator, and we get 216, 416. Okay, cool. So that's our baud rate divisor, right? But however, we want our integer portion of it, and we want our fractional portion of it, right? So for the integer portion of it, we could already see that our UART IBRD baud rate divisor, that's going to be equal to the fractional part of that baud rate divisor, so that's just 260. And then our fractional part, which is our FBRD, that's going to be the decimal point, right? So 0.416 times 64 because of the bit, and then once we do that, we add by 0.5. And we get that resulting number to be 27.16. And then pretty much all we have to do is we just take this portion of it. So if we, well, technically we're just rounding, right? You could consider it rounding, but we're just technically want the integer portion of it. So that's just 27. Okay, so now we found our two required variables that we needed, and yeah, let's get back to our code now. Now that we pretty much have our UART IBRD and our UART FBRD, pretty much what we want to do now is essentially enable the clock to UART module 0. So that's what we did here, right? We enabled it to module 0, and then we allow for the clock to stabilize. So module 0, module 0. Then after we disable the UART by clearing the UARTin in the UART register. So that's what we do here. We do this by essentially clearing the bit, right? So when we want to clear bits, we use the AND and then the sign here. And then pretty much what we want to do is we want to write BRD to the UART IBRD. So pretty much we want to write our baud rate divisor. And remember, from as I previously mentioned, that our divisor has two parts, right? It has the integer part and the fractional part. So that's pretty much what we're doing here. We're setting the baud rate divisor to both those parts. Then we want to essentially write the UART line control, right? So pretty much for that we have an 8-bit, right? Which is the that 8-bit is essentially it's the data length, right? And then we want, there's no party, right? So we set it up for no party. Then we put a 1-stop bit, and then we do the FIFO. Then the next part, essentially, we configure the UART clock source, right? So the clock source from the system clock, right? So that's what we pretty much did here. We configure that part. And then for the next part, pretty much all we do is, we essentially enable the UART by clearing the UARTin and the UART register, and then we pretty much enable the TX and the RX that essentially we need in the code in order for the two devices to have communication with each other. So yeah, this is pretty much all the UART setup part. Yeah. Now, in the next video or the next experiment, we'll see how to set up the other setups for this. Is for eventually we're going to lead up to experiment 3. Okay, so now in experiment 2, we're going to look at the other setups that we need to essentially get the sensor to work. So pretty much first, I want to go over the setup timer. So essentially for the setup timer, we enable the clock timer module. And as you can see, we do that in line 124 and 125. Um, then we disable the timer, right? And by clearing up the bits for that. And again, we know that we're clearing up the bits because of this here. Then we configure the timer, right? We split into two 16-bit timers. That's essentially what we're doing here. Then we configure the timer for the big board. It's timer 0. So we configure timer 0 mode, right, to the countdown, the timer mode capture, and the timer capture mode edge time. Then next we configure the time event mode, so the rising and falling, right, or both edges. So for us, right, in this lab, essentially what we want to do is we want to do both edges, right? We want to see when it's rising and falling. So and that's essentially going to be part of the echo, right? That essentially we're going to use to control our 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 sensor. So yeah, that's that. And then we want to configure the load, right, to the timer. We set timer 0 to configure that load to FFF. Then we set the prescaler, right, to 0FF. And then essentially lastly, what we do is we enable the GPTM timer. So we enable the timer essentially. This timer, and again, the sensor. This pretty much is enabling the sensor to read in that timer. So essentially, the timer is going to be what times the essentially when the sonic waves, the sound waves leave the transmitter back to the hit the object and then back to the receiver. So essentially, that timer times the time that it takes for those sound waves to travel to and back the sensor. So yeah, that's that part. Um, and then next, let's talk about the setup GPIO, right? So for the setup GPIO, we need to enable the clock to the GPIO modules. So essentially, for the UART, right, which I previously talked about, that's port A and pins 0 and 1. So those are the pins that the port and the pins that we're gonna use to enable our UART. Port L is essentially port L pin port L pin 4 is essentially going to be our echo pin. So that's going to be essentially what sends out the echo, and then port L pin 5 is going to be our trigger pin. Okay, so essentially we need to enable those, right, in order for us to use them. So we pretty much have to do the setup GPIO. So again, first we have to enable the clock to the GPIO modules. Then we have to allow the clock to stabilize, right? And then we have to do the port control, right, for both the ports. Then we have to essentially clear the ASCVL bits to 0 to select the regular I/O. Then we essentially do the pin direction, right? Because it's an output, right? So the only output that we're going to have is pin 5, because essentially pin 5 is our trigger, right? So port L pin 5 is our trigger. And then lastly, we're going to need to enable, right? We're going to need to enable all the data pins that we've used. So again, for port A, pins 0 and 1 are going to be for our UART, which I previously mentioned. So that's going to be, that's what we have to enable those pins. And then for our port L pins 4 and 5, that's going to be used for our sensor. So that's why we have to enable the GPIO. Okay, cool. So then lastly, what we essentially had to do was use this measure T, right, to measure the time or the pulse width in order for us to determine the distance, right? Because we need that pulse width or that time to essentially determine our distance. And we'll see later on in the third experiment how we're going to use that. But first, let's define that part. Okay, So for the double measure t, which is measuring our time or pulse width, pretty much what we have to do first is we have to clear the GPTM timer and capture mode event by writing it to 1. So again, our timer that we use is timer 0. That's what we're doing here, and then we're waiting we then wait for to capture the rising edge by checking the GP TM raw interrupt status, right? That's what we do first. And then next, what we have to do is we have to set the high edge from the two registers. Then we have to wait for to capture that falling edge, because remember, we're essentially using our echo, right, to capture the rising and the falling part. So that's what we have to do there. And then we have to wait for that capture falling edge, right, by checking it. And then for part 6, we set the low edge from the GPTMR to the registers. So yeah, that's what we're doing in part 6. And then lastly, we want to calculate delta t, right? So how do we calculate that delta t? Okay, so there's going to be 2 conditions, and it's preferable if I actually draw it out. So let's get to that. Let's get to that part of the video. Okay, so here we have sorry, I could get that out. Okay, so here we have our a graph here that says for the counter and the time, right? So the highest the counter can go is essentially 0x FFF. So that's the highest that the counter can go, right? So that's our maximum. And pretty much what's happening is that let's say there's the pulse width that's happening, right? So where it goes down, where it rises up and then comes back down to 0. So essentially, there's going to be 2 cases. So the first case is where the high edge is essentially bigger than the low edge. So in that case, right, we want to solve for this distance between here and here, right? We want to solve for that part there. And how would we do that, right? So pretty much to solve for that, we would just do the high edge, right? We would just do the oops. We would just do the high edge, right? Minus the low edge, right? And then times the timer frequency, because that's how we find delta t, right? So the high edge minus the low edge times 1 over the timer frequency, and the timer frequency is 80 hertz, 80 megahertz. So yeah, that's pretty much the so the timer frequency. Again, I'll put that here. The timer frequency is equal to 80 megahertz. Okay, so yeah, so that's case 1. And then case 2 is essentially when the low edge is higher or is bigger than the high edge. So in that case, right, pretty much what we have to do is we have to find the distance from this point here to here, right? So that's going to be just the high edge minus 0, right? So we can put minus 0. Let's turn this into that. So minus 0. Then we're going to add, right, because we want this entire part here. So we want this portion and this portion here. So plus, and then it's going to be 0, right? 0x 6f's f, right? And then from that portion there, whoops, sorry, we're going to get subtracted by the low edge, right? We're going to subtract it by the low edge. And then we're going to multiply that by our timer frequency, and then that'll give us the delta t for that case. There's 1 over the timer frequency. So yeah, essentially all we're going to do now in the part 7 of our code is we're just going to turn this into code, right? So how are we going to turn this to code? So we're going to have 2 if statements, or an if statement, an if else statement that says if the high edge is bigger than the low edge, right, then this is going to happen. Case 1 is going to happen. And then if the low edge is bigger, or else, right, because else is just basically the other option, like else if the low edge is bigger than the high edge, then this was going to happen. And yeah, that's pretty much it. Okay, but yeah, so that's pretty much everything for experiment 2. Now in experiment 3, we'll see how this all comes together. And yeah, let's hop on to the next experiment. Okay, so now it's experiment 3, right? And for experiment 3, pretty much what we have, right, is we have all our setups here. We have all this stuff here. Pretty basic. We're calling back our UART timer, our GPIO, our measure T, right, which is what we previously covered in all the other videos. And then we have our system clock, right, which is up here, which we had set to 80 megahertz, right? Yeah, we pretty much have all that stuff up there. And then now let's get into the actual portion, right? So, as you may recall, I said that our trigger is port L, pin F, which is what I had initialized here, right? I had said that here, and then I also initialized a string variable, right? That string variable is essentially because pretty much what we want to happen is that when the sensor essentially times that distance, right, and then sends that data back to the computer, we want the computer to then calculate the distance, and then pretty much what we want it to do is essentially display that distance on the PC, right, or on the computer. So we wanted to display it in a string format, so that's why we have that string character. So yeah, and then in our main function, what we have is our pulse width, right? We initialized a couple variables: our pulse width, our distance, and yeah. And again, we pretty much are just calling back to the other setups that I had talked about in the other 2 experiments down here, right? These 2 setups. And then here is using our print, our string, right, to print out this string here, which is the project for this class. And obviously it's called the ultrasonic sensor. And this is basically calling, this part here is calling back to our UART print string function. And as you may recall from previous experiments, that function is here. And all this function pretty much does is basically has a communication between the UART and the computer, right? And yeah, it allows the string to basically print out. So that's what that function does here. Okay, so yeah, back to our main part. Pretty much what we want to do first is we want to set the trigger pin to low. We want to wait 500 milliseconds, then set the trigger pin to high for 10 nanoseconds, then wait, and then by doing that, right, we set our trigger pin to bit 5 because, as I said, it was pin 5 that essentially we're going to use. Then we set our trigger pin to low again, and then we wanted to essentially call to the measure T to get the delta T on the echo pin, right? And as you may recall, what we did here was essentially we calculated our pulse width. So the distance, right, that we want is the pulse width or measure T, which is what we previously found. So yeah, that pulse width times the velocity of sound. Then we're going to divide it by 2, right? So why are we going to divide it by 2? So pretty much we divide it by 2 because essentially we want the distance from the sensor to the object, right? But essentially that time that it takes for the sensor to, or the timer that the sensor reads is essentially the time from the sensor to the object and back, right? But pretty much all we want is the time from the sensor to the object, right? Not back. So therefore we just divide it by 2. And then pretty much down here, all we're going to do is we're just going to display everything on the, here. What we're going to do is pretty much just display everything on the PC. So yeah, that's pretty much it. So yeah, let's take a look at what that looks like when everything is all together, and let's take a look at everything that we have set up. Let's get to it. Let's get to the results for everything. Okay, so now let's look at the results for this lab experiment. So pretty much, as we can see here, I have my TIVA board, I have my breadboard, and connected to my breadboard is the ultrasonic sensor module, right? And then here's our transmitter, and then here's our receiver. And as I'm not sure if you can see that, but connected to this is our circuit. Sorry about that. It's connected to our circuit here. And then pretty much it's connected to the 2 pins on the TIFA board. It's connected to PL4, PL5, which are our echo pins and our trigger pins. And then here are also it's also connected to ground and to power. So yeah, so pretty much like I said, right, we're gonna put an object in front of it. I put this little bottle of hand sanitizer, and then pretty much, right, if we look closely, it's around the 5 centimeter mark. So pretty much this this sensor here is gonna basically read the distance from the sensor to the hand sanitizer and back, right? So all I'm gonna do is now I'm going to press the reset button here. And then if we look at the screen, here, let it focus a little bit. Let me get closer actually. And then if we see here, right, it essentially does do that reading. It reads that it's about around the 5.24 centimeter mark. And then here it also displays the amount of times it's going, right, on this side. And then here's the width, and then in microseconds, and then the distance. So yeah, that's pretty much it. Essentially, yeah, that's our distance, our width, and that's essentially what we wanted. And then in the background here we see our code. So yeah, that's it. Again, the sensor, all it's doing is just reading the distance from this point here to there, and it's just displaying it on the module. So yeah.